Good. Web and software bugs. We're going to talk about bugs and vulnerabilities. Some of the learning goals for today. Web applications are just regular applications that are a bit more complicated, but they do have a lot in common with regular applications, including a lot of bugs and vulnerabilities through all the different layers of the stack. Understand the impact of processing attacker-controlled data. Whenever you're handling data that comes from the attacker, you have to be careful when you're writing applications. And then differentiate between types of bugs and what potential attacks they enable. We'll start on the web application side and then move on to the software and system security side. First one, then the other. Because web applications are slightly easier to get into, and then we'll generalize. So on the web application security side, we're generally looking at the OWASP top 10, and that's the main thing I want you to take away from this course. When you're working with web applications, consider the OWASP top 10. The Open Web Application Security Project, they are looking at some of the key issues that repeat again and again. And these are the main attack vectors in applications, and also the most common issues that you will be having in your applications. Then looking at arbitrary code execution on the web application side through, for example, cross-site scripting, SQL injection, LDAP injection, and command injection. These are all forms of arbitrary code execution, where an attacker can execute some code on behalf of your application, either on the client side, on the server side, or a mix between the two. For web applications, one of the difficulties is that it's not just running in one application, but a web application, if you're logging into Gmail, there's a backend that is running on the Google server, and there's a JavaScript front end that is running on your end. But essentially, this is one application that consists of multiple parts that are running on different ends. And an attacker can get code execution either on the server side or on the client side on your end. And it makes this a bit more difficult from the context. But from the software side, it makes this a bit easier, as we're not looking at memory corruption, buffer overflows, and whatnot, as in other systems-oriented languages. But we're looking at high-level command injection or code execution in JavaScript, in SQL, in LDAP, or something else. So who has heard about OWASP before? Quick show of hands. Okay. In what class, or in what on what subjects? Yes?
I took a course like this, ethical hacking. So.
A course?
Yeah, it's like an exchange last year. It was ethical hacking. So. Yeah,
okay. At EPFL?
No, in DT in Denmark.
Okay, cool. Who else? Like, this is your cheapest way to get candy. Yeah.
It was the CISO's way of telling us what to be aware of when developing stuff in the application.
Okay, cool. Yeah, this, the air properties of candy is not great. Cool. What else? Yeah.
Google cybersecurity course
Uh
online.
huh. And they covered OWASP. Too much friction. Cool. So several of you have heard about OWASP and different kind of OWASP. You've heard about the top 10, right? Not just about the Open Web Application Security Project, right? Because they are mostly known for their top 10. So there's a lot of they offer a lot of useful aspects, such as the top 10, which we'll go through today, but they also offer different tools like SAP, the attack proxy that allows you to test web applications, different kind of testing guides, and learning material. So if you're interested to go deeper into this material, for example, you want to become a web application pen tester, go read through these top 10 and any kind of extra material that follows from there. The most recent update is from 2021, I think. There should be a new update this year. There's cross-references to CWEs, common weakness enumeration, and we'll list some CVEs as well, common vulnerabilities and exposures. So a CVE, to get back to the jargon and abbreviation, a CVE is a unique number for a vulnerability. And in the end, this is just a number that consists of CVE, the year, and then an increasing number that uniquely identifies a given vulnerability. It doesn't say anything about its severity or whatnot, if it's exploitable, when it is exploitable, but it just gives you a unique identifier for a vulnerability. A CWE is a class of issues. So a set of weaknesses, such as a buffer overflow, is a CWE number, right? So stay aware or be aware of the difference between CVE, which is a unique vulnerability, and CWE, which captures a class of certain security bugs or issues. We'll now walk through the different OWASP top 10 numbers and give a couple of examples so that you can play with those in a bit more detail and be aware of it. The most common issue is broken access control. Access control enforces a policy such that users cannot act outside of their intended permissions. So, for example, a web application should verify that you are logged in as administrator before allowing you to delete posts of other users or whatnot. Failures typically lead to unauthorized information disclosure. For example, an user is not logged in being able to download certain data, certain aspects, accessing documents or whatnot, or even being able to modify other aspects. There's a bunch of CWEs that are grouped under this issue. The CWE 200, exposure of sensitive information, 201, insertion of sensitive information, and 352, cross-site request forgery, which we'll talk about in a bit. A good response to this attack vector is to just reduce the attack surface, right? If you're writing a web application, it shouldn't be allow by default or deny by single enumeration, but deny by default. Right? So there's a common security practice that you deny everything that you do not explicitly allow, which means if everything is denied by default, you have to explicitly allow certain aspects, such as access to this resource only if you're logged in or whatnot. Implement access control mechanisms only once, and then reuse them throughout the app. By, for example, like validating a session or inserting a session token or something like that. So if you're not logged in, you're automatically redirected to the login page. You have to log in, create a session, and then through this session, in all the other parts of your application, you only have to validate the session, and you no longer have to validate the login credentials. Log access control failures on the back end, not at the front end. So you shouldn't, if there's an error, you shouldn't disclose this information to the users, but log it somewhere on the back end. And then last but not least, rate limit API calls. So if you have different kind of web API calls that you allow external parties to fire, make sure that you rate limit them so that they cannot exhaust your resources. An interesting recent real-world example is a bug that allowed everybody to access Google Drive files without the original access permissions. So in Google Classrooms, a teacher can create a classroom and can add students to that room. Students can then submit their Google Docs to the classroom, and the teacher becomes the owner of the document. So there's an ownership transfer. Then data is being transferred into the shared classroom Google Drive. Now, when this happens, when the student submits a Google document to the classroom, the ownership is transferred from the student to the teacher, or that was at least the intention. Now, You see the HTTP request when a student submits a document, and in bold you see the Google Drive document ID of the submitted document. Unfortunately, Google actually forgot to check the owner of the document ID that was submitted. So a student or a fake account could submit, or an account that was a student in their classroom could submit an arbitrary ID and giving the teacher access to that Google Doc, even though the student was not the owner of that Google Doc. So this was a very interesting attack vector where Google simply forgot. They validated the session of the student. They validated that the student was a member of the classroom. They validated the teacher that was owning the Google Classroom, but they didn't validate that the student actually owned the document that they were passing on to the teacher, resulting in the exception afterwards. So it was a very interesting bug, and these things can actually happen even to large companies like Google, and even today, right? So it was just a couple of months ago. This is a very, very recent attack that happened. Cryptographic failures, that's another one of the favorites. When you are validating an application or a web app, determine what kind of data you're dealing with and how it needs to be protected. Do you need integrity protection? Do you need confidentiality? Do you need to protect the data in transit or at rest? If it is in transit, slap on TLS and you should be good. Maybe you need to validate certificates. For example, if you are creating a mobile application, you can pin the certificates or whatnot to get extra protection and so on. But often you find much simpler vulnerabilities, such as hard-coded passwords, broken or outdated crypto algorithms, and another favorite, using insufficient entropy. There are several classes of researchers that made it their job to find locations of insufficient entropy. One of my favorites was, there's a couple of years back now, in Debian, the random number generators were initialized through semi-random data or memory that was laying around in the application. A compiler complained that this was an unsafe read of that data, and then it commented out that source of entropy, thereby reducing the entropy of the OpenSSH key generation to only the process ID, which was usually between 100 and 1,000. So a lot of the private keys that were generated were actually the same. Like several % of private keys on the internet were just the same. It was a very interesting bug due to the massively reduced entropy. If you are designing your web applications, just stick to the default cryptographic algorithms. Make sure to only store the data that you actually need. Like be very conscious of what data you store and what data you have. Periodically ensure up-to-date algorithms and disable any legacy protocols that may be running. The third one is injection or any form of injection. Code injection is possible when attacker-controlled data is handled incorrectly and ends up being parsed as code. So all the code injection attacks are the same. Right? The attacker submits some form of data, and the application, due to whatever bug, interprets this data as code. And we'll look at different variants of this a bit later in the class. You can reduce your attack surface by shifting to a safe API, sanitize user input through validation and escaping. Like make sure that you actually get what you expect. So for example, if your web application expects some JSON file that contains a string, make sure it's actually a string and not an array of strings, right? Or a hash map of strings or whatnot, that it's the right and correct data type. Validate input whenever possible. Make sure that it's in a range that you expect, and then escape any remaining characters when necessary. An interesting angle of injection is the cross-site scripting, where, for example, an attacker prepares malicious code, gets a user to click on this malicious link to then execute code on behalf of the web application and the user session, right? So this allows the attacker to execute the banking app on behalf of the user in their context. Yes, please.
What's the difference between sanitize and validate the inputs on the last slide?
Sanitize is you, for example, escape certain characters. You make sure that there's no quotes or so I think this should be indented, right? Sanitize user inputs through validation and escaping. Validation is you make sure it's in a certain range, it has the expected values, and then you escape. So just indent the last two. You already got one, but you get another one. I'll keep trying until I hit. No, this is too far. Cool. There's more on this later, so we'll cover this in a bit more detail after we're through. By the way, regarding the candy, I picked those that you cannot buy here because these are from my recent trip in the US. So these are all candy you will not be able to find in the stores here. So maybe ask more questions in the second part. Insecure design, the fourth category. And I know this is a bit a dump of categories, but we're going to go through more of them in detail afterwards. Insecure design is a very broad category. Think of this as a catch-all for anything that just looks weird or iffy or is design related. You can prevent this through by bringing the validation or security discussion into the design process of the web application from the beginning on, and then carry it through throughout the whole design of the web application. Use threat modeling where feasible, and segregate and compartmentalize where possible, focusing on the principle of least privileges. Security misconfiguration, another common one, right? The security configuration or the configuration of the web application or the web application framework is part of your attack surface. Software is getting much more configurable. An email server has like 2 billion different settings that all of which can result in different kind of security issues and vulnerabilities. Be very, very careful in how you configure it. Keep track of the configuration and make sure that you document the configuration. After initial testing, harden the configuration and make sure that you've optimized it so it's the best possible form. An example I wanted to discuss is this Nginx misconfiguration, where if you're looking at Nginx, it's a very common web server and proxy. And in this example here, it's configured with a root where the different configuration files lay, and then it gives you a directive for hello.txt and how it is being served. Now the issue here is, what do you see? Do you see it?
Hello.txt must be div. Hello.txt may be just directory, not file.
A directory? No, that's not it, but that's a good option. Nice. What else? Yeah? It gives information to the internal networks. No. Yes?
I think being the root etc Nginx is quite open, much more restricted, because otherwise it's going to try files inside the Nginx directory.
Yeah, I think this is the correct one. You have a special route for hello.txt. So if you get hello.txt, you serve hello.txt. But the default location directive for the root directory of the web server is missing. And if this is missing, Nginx will default, which is an insecure default, to the root directory, which allows the attacker to download the configuration, which is likely not too bad. But if you have another subdirectory in there that contains your private key for your TLS keys, then yeah, you're out of luck. Last component, I'm going to spend 5 more minutes for the next components, and we're going to do the break. Vulnerable, outdated components. Keep your software up to date, essentially. Like this is just a common issue that we've already discussed. Software may have known vulnerabilities. Make sure that you update all your software that you're running. Identification and authentication failures. Make sure that you validate the user's identity. Authenticate and session management is critical to any web application. Just keep track of it and make sure that this is done in the right way. Reduce the attack surface through two-factor authentication. It's a common approach. Check for password hygiene and limit or rate limit repeated attempts. Software and data integrity failures. Software and data integrity failures relate to code and infrastructure that does not protect against integrity violations. For example, you're bringing in plugins, libraries, or modules from untrusted sources. The prime example here is WordPress. Who has set up WordPress instances before? Wow, this is really sad. There was like 2 hands. Back in my days, 80% of us who were studying were like working as web application developers in our spare times, and everybody would have set up a WordPress instance. So WordPress is a very bare bones framework to display web pages, and you have to use a bunch of different plugins, right? And the plugins are where all of the vulnerabilities are. So make sure that you're aware of what plugins you use and keep updating these plugins along with the main system. Security and logging, monitoring. Make sure that you log any kind of severe issues and violations so that you can go through them later on. Ensure that you have an actual audit trail for these applications. Last but not least, before the break, server-side request forgery. In the end, you can abuse the web application as a confused deputy. Confused deputy can be tricked into doing things on someone else's behalf. So your web application that is running on a server side will likely have to issue additional requests, for example, to the database server or to other servers, either on the internet or on the internal network. Now, your web application has access to both internal and external the internal and external network, and if an attacker can control the request, the attacker can gain additional privileges from that. So this is a pretty common way to get around firewalls because of the web server being dual-homed in both locations. Right, so server-side request forgery. These trends emerged, these trends change, right? So in 2017, it looked a bit different than in 2021, 4 years later. So some of the issues have become more dominant, while others were mitigated through new mitigations or just are not getting as exploited anymore. So OWASP, the Open Web Application, the framework, pretty much they count the number of vulnerabilities and then they group it to highlight the most dominant attack vectors at any given time. Yes, please.
How are these trends sorted? Is it based on how many times it happened in the past?
Yes. Like mostly how many times it happened, how many times it happened in the last couple of years, but also it tries to highlight if something is increasing, it is being pushed up. In 2021, they also started including community feedback. So for example, server-side request forgery is being added on community feedback. There's not that many attacks yet, but based on the community feedback from the web application practitioners, they brought up that this is actually more and more of a threat. Yes?
Does it take into like the impact of the attack into account to classify them?
Yes, this is being ranked as well a bit. But it's usually for web applications, they're so shitty. As soon as you have a bug, it's game over. You get access to most of the data. Yes?
Is there also a ranking for how dangerous the attack
What attack?
How dangerous, like how feedback?
it's very hard to do this in general. So the same bug type can be more or less severe depending on the context it runs in. So pretty much all of these can result in pretty severe compromises. I hope I don't kill anyone. Nice. Intercept. Last but not least, right, mapping to different the COM402 classes. So if you need a mental mapping between the OWASP top 10 that we just discussed and different kind of COM402 classes, you can look at this. We'll take the break now. We'll see you at 20 past. We're now going to shift gears a bit and talk about arbitrary code execution, going a bit more into detail of these different angles that we discussed. We've given, previously we've talked about a broad overview of different, the different web types of vulnerabilities. Now we're going to go into arbitrary code execution, still on the web side of the context. Code injection in general is possible whenever user-supplied data escapes control. So in the end, the user or the attacker supplies some data, gives some data to the application, and then the application misses a security check or misses a validation, and then this data is being interpreted as code. This can happen in SQL, LDAP, OS command, XML, XSLT, SMTP, and whatnot. Like all these different kind of protocols that are being called from your web application. So the underlying vulnerability is that special characters in user inputs can trigger an action in the context that then switches to kind of running the rest of the code through an eval instead of just treating it as data. So it becomes code instead of data, thereby being elevated and interpreted as data. Attacker-controlled data becomes code that may be abused to escape the intended behavior of the original code. Let's do an example, right? Not all of you have heard of SQL. SQL is the structured query language and can be used to interface with databases. It's already a bit dated, so this was being developed in the 70s and 80s and saw its main rise in the 90s, but it's still the dominant way to interface with large set of data. Databases are organized in tables. Think of a table as a Google Sheet or an Excel sheet where you have a name for the sheet, such as a table users. And then the tables are organized in rows and columns. Columns have names, for example, first, last, referencing individual fields of the users. And then you can use select to select individual roles across all these different columns that you select. So with the example, select first, comma, last from users where city equals Lausanne. You would tell the database engine, select the two fields, the two columns, first and last, from the table called users for all the different rows where the city column equals Lausanne. Right? And then you can iterate through the set that is being returned. So it returns the columns first, last from all the rows of table users which have the value Lausanne in the column city. Now, if we turn this around and look at SQL injection, an web application may create a SQL string as follows. Is a string that is being sent to the database. Request equals select user from tuser, where user equals get user, and password equals get password. What you see here is these beautiful quotes. Right, here's a double quote that tells you this is a string. Then you have a single quote, and you concatenate it with whatever is in this variable, and then you continue concatenating it. And then you run a MySQL query using a connection you've established before to the database server. You send the request. If there's no single valid valid entry, you abort. Otherwise, you're being authenticated as the authentication succeeds, right? So, for example, I could try to log in using my username and password let me in, which is one of the most common passwords. And the string, like that the web application would send to the database is as follows. Select user from tuser, where user equals Ganimo and password equals let me in, and I will get a row, and the system would say all good. Now, how can we exploit this? Does anybody see the issue who has not seen the SQL injection before? Go ahead.
Like maybe we can just set the password in, just insert and the massive, and then come back to something that works.
Yeah. I think you already got this one though. That's why it deflects. Cool. What you can do is you can inject, for example, at the username, because we don't even know if the username is correct, right? So instead of the username, we insert end quote, like a single tick, and then %20, which is a white space, and then 2 double dashes, which turns the SQL string that is being sent to the database into select user from tuser, where user equals Ganimo, end quote, and then tells the database server, please treat the rest of this line as a comment. Right? And this will automatically validate the password, validate the session. The single quote ends the string. We start a comment, so there's no need to know the correct password, and we can just log in as a user. Yes, please.
Don't we also need to add a double quote to close the whole string in request?
The double quote?
Yeah, the start of request.
No, we don't need the double quote, because the double quote, this is being added from the, like we're only changing whatever is in the field of the variable. So the double quote, we could add double quote, but we don't we don't care what the rest is, right? Because the database sees, like, this is essentially the little program that is being sent to the database that tells the database, please execute this program. Oh, and by the way, this is a script that is being executed by the database, and the rest here is just a comment. Right? So you won't need to look into this. Other questions? There's different forms of SQL injection. Stacked SQL injection can combine multiple queries. So instead of ending with a comment, just for login, we can end the current SQL command. So we can end the select and then say, oh, by the way, just drop table users, which would delete all the users' passwords and everything else. We can also do blind SQL injection if we don't get anything in return. So if the web application doesn't copy the data back to the attacker, the attacker could use timing, select first, last, blah, blah, and the injected string becomes where city equals Lausanne, tick, union, select if substring password equals character 50, wait for 50. So you just wait for a certain amount of time, and then you can use the timing difference as a side channel to infer what the actual password is, and then leak the password 1 character at a time. Because if you hit the correct password, it will take a little bit longer. So you can iterate over all the possible, like password, over all parts of the password 1 character at a time, and then iterating through all the possible values in the password. It's a pretty cool way to leak concrete values from a database if you don't have access to it. Okay? Cool. LDAP. So LDAP, think of it as a fancy way to keep an address book as a service. So this was the classic service for like address book for companies, including roles, management, passwords, and everything else. It's like a directory protocol, and you can use it to query these different directories. So for example, EPFL, people.epfl.ch gives you access to the EPFL LDAP under some asterisks, right? Which allows you to query different users, different units, different research groups, and so on, who is in what room and whatnot. And LDAP is similar to SQL. You can search expressions, and you can combine logical conditions with parentheses and whatnot. The ampersand is the AND operator, the pipe is the OR, the asterisk is the wildcard. So for example, AND name equals John, asterisks, anything else, any name that starts with John, and status equals prof. So the name starts with John and status is prof. And here, for example, you could use a name admin, close parentheses, open parentheses, and, which would then validate to name equals admin, and is always true, because this is just an AND by itself, and then the password equals blah, 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 blah is ignored, and you've just logged in as administrator on the system, or on this web application, right? Same pattern as for SQL injection. Yes, please.
Is LDAP implemented the same way as SQL, as in you'd have like a LDAP engine or LDAP server running?
Yes, right. LDAP is also a server. Right. I said asterisks apply with people.epfl.ch because EPFL has an active directory, which is the Microsoft bastard version of LDAP, which is somewhat similar but not exactly the same, but they do have an LDAP backend for legacy services and whatnot, so it's mostly that. Yep. There's blind LDAP injection as well. So for example, this Joomla bug from a couple of years ago was a nice way to for an attacker to guess password one character at a time, similar to the blind SQL injection that we had before. If you look at this more recently, but still haunting us, Log4j is one of those vulnerabilities that allowed attackers to inject arbitrary code as part of an external dependency, which was a logging framework that allowed data from, like, when data was being sent from the attacker, it was interpreted as part of the logging process, and unfortunately, as part of the LDAP string, the attacker could supply extra Java classes that were then downloaded and executed in the context of the web application, which sounded like a nice feature to have, like allowing LDAP login as part of the framework, but then it resulted in arbitrary code execution in pretty much every single web application that was out there, which is not great, right? Also, Log4j, the issue here was that this was an extremely ubiquitous logging utility. Everybody was using this to like dump logs into different files. Unfortunately, the logging feature allowed you to trigger extra actions that then caused an LDAP query. And as part of the LDAP query, if it was interpreted as an LDAP query, it resulted in arbitrary code execution. Not great. So yes, this happens again and again. Command injection is another one of my favorites. Like if you run runtime.exec, the Java method to execute other programs. Let's say we are on Windows, we create a string, command equals new string that consists of 3 parts, command.exe execute to run the command interpreter, /c, which tells it execute this one command, and then the command is dir for list directory and the chosen directory. If the chosen directory parameter or variable is just photo, you get the list of all the photographs or of all the pictures in the directory. If it is photo and remove directory, silent, recursive photo, you no longer have photos because as a side effect it executes this other command as well, right? And again, here the idea is that Like the programmer intended that this was just an identifier for a directory, but it allowed extra commands to be executed. So it wasn't just data, right? The programmer was interested in data. Which directory do you want to select? But allowed the attacker control over a string that then allowed inserting extra parameters that were added here. And here, like you see that we can concatenate a second command after the first command, allowing the attacker these extra capabilities. For cross-site scripting, like JavaScript code is being injected into web pages. The context here is HTML and JavaScript to, for example, steal session cookies, display forged forms, or just get arbitrary code execution on behalf of the web application. Let's say you're a young and eager PHP developer. You are simply like getting a parameter, EID equals get EID, so this is getting one parameter from your URL, and then you're displaying employee ID is EID. So here what you're doing in this application, you're essentially taking a parameter that is encoded in your URL, and you're embedding this into your web application. Here you're not vetting this in any way or form. So raw user data is reflected in the HTML response. Like the server sends back anything that is being encoded in the URL in this parameter, including HTML characters like the smaller than or larger than. Right? So this allows the attacker to include arbitrary code and encode it in the URL itself. Now, if the attacker sends you this encoded special URL, this allows them to execute JavaScript code in your in the web application in your context. Right? So let's say you're logging into your web online banking application. If the attacker controls this a parameter there, it allows them to then take over your session and remotely control it, for example, clearing your bank account. There's three types of cross-site scripting reflected. This is what we just discussed, right? The attack is sent in the request and reflected in the response. So nothing is permanent on the web server, but it's just being reflected through the web application. And for example, if you write a URL like this, fancy web app, question mark, EID equals script alert hello from JavaScript, this would be executed on behalf of the user context when they're logging in. Stored cross-site scripting, yeah?
Actually, like the browser in practice automatically encode the HTML characters in this URL, so it wouldn't really render, it wouldn't really trigger the success. Like the characters.
Depends. Encoding depends a bit on what you do.
Like Chrome automatically, like Chrome, Firefox, Safari automatically encode like before it's created, like all the characters of HTML. So
this doesn't protect you from the cross-site scripting. Like I'm giving here a simple example that is being reflected. There's some partial filtering, some rewriting. So if you type it like this, then Chrome will replace it.
Yeah, but like as an attacker, you can't make a victim browse this URL if the character is not URL encoded. Like you can automatically URL encoded by Chrome.
Right. Let's take this offline. It depends a bit on the encoding. This is how reflected cross-site scripting attacks works, but again, it depends a bit on the context. Stored cross-site scripting, the attack is stored on the server, returned on certain responses. For example, for all the users that download or browse a certain page, the malicious code is being returned. For example, in a web forum, this is a common attack vector. There's also DOM-based cross-site scripting where the attack happens on the client side, and the client, like for example, you're in Gmail, somebody sends you an email. The Google, the server side pushes this to your client, but then the JavaScript application has a bug, parses the email, and then allows a cross-site scripting attack in the on the DOM on your client side. Protection against injection. One angle is deny by default, otherwise inspect the received data twice. You see the same pattern, deny as much as you can, deny all, and then just validate individual aspects that come in. First, when you're receiving input, when you're receiving data, do input validation, refuse anything that you don't need, refuse any data types you don't need. You could use a regular expression, although this is not necessarily recommended. Use existing frameworks for validating. Another aspect is encoding data, which is pretty much what you mentioned as a mitigation. Whenever data is being sent that contains potential malicious characters, encode them in any way or form. For SQL, if there's a single tick, turn this into a backslash tick. HTML, you can use plus %LT for less than and % greater than. LDAP, you can turn the parentheses into special escape characters as well. For SQL injection, the only thing you should actually use, apart from validation and escaping, which is not the best option, is to use prepared statements. For SQL injection, prepared statements separates the control channel and the data channel, allowing you to send the little script to the database server and telling the database server, hey, by the way, I'm expecting 2 parameters, name and password. And then you can prepare the statement and set it set string 1, set string 2 to actually submit the 2 parameters that were left in here. Right? So that way you can separate the little script that you're running and the actual data that you're sending. Cool. So for web application security, web applications take user input and put it into many different contexts. Be sure to refuse by default, right? Always escape, encode anything that's dangerous, separate code and data, as with SQL prepared statements. Oftentimes, good web application frameworks already take care of filtering in any different ways or forms. For the different requests, or for every request, check if the requesting user has adequate permissions and validate the session. If not, redirect to the login. Questions about web apps? Okay. Yes?
Just a question. For LDAP, is there any such thing as prepared statements? Because you also have queries.
I'm not aware of it. Maybe, but I'm not LDAP is not really used much anymore. It's still lingering around a bit. I have no idea if.
So it's always like a legacy issue.
Well, depends. If you're in a corporate environment, you'll likely be using LDAP and querying LDAP servers, but it's a bit. It's more niche-y, I'd say.
So we have to do it ourselves when we get a query.
I guess. I'm not aware of prepared statements for LDAP.
Okay.
But you can validate that there's no
Escape.
escape characters. Yeah.
Okay.
Cool. Anything else? Software security. So we're going to go on a wild ride over the next 20 minutes on buffer overflows and different kind of mitigations. We're going to breeze through buffer overflows a bit because we've already covered it, at least to some extent, in the memory safety classes. Here we're going to look at it from a bit of a security perspective. Software vulnerabilities exist. Programmers are not perfect. All software has bugs. Some of these bugs are vulnerable, and sooner or later adversaries will find a way to exploit these vulnerabilities in nice ways or forms. For those that never worked with programs before, programs are made of instructions, and data that are loaded somewhere into memory. You can think of a process that is running as a flat array of memory, a large array, where some parts of this array are individual instructions, other parts of this array are data and references to different data and instructions. Processor has a set of registers to store the data that it's currently working with. One of the important registers is the instruction pointer, which points to the address of the next instruction that the CPU will execute. Other registers contain pointers or results of some calculation. There's a lot of different assembly instructions. Move moves data from an address or a register to an address or register, and there's add, multiplication, division as arithmetic calculations. Quick systems programming reminder that you've likely seen before. We usually split a process into code, different kind of code section, a heap section, a stack section. There's code with code pointers in there, and on the stack, the return instruction pointer on the stack will point somewhere into the code section where data is being sent back and forth. I'll now walk through a simple example. We've got this vulnerable function, char buff32, put as your username, get as buff, which means, or asks, will print on the screen your username, question mark, and then reads in a buffer. The maximum length that we have on the stack here is 32 bytes. So we can store a string up to 32 bytes. If we're beyond the length of 32 bytes, we'll end up overwriting anything that is adjacent to it. Remember, C does not have any kind of memory safety. So as we are calling from main into this code, we're at the instruction of call vulnerable in the machine code on the side. We are opening up a stack frame with these instructions. So we're adding space on the stack, which allows the function to actually work through the data. There's a stored base pointer in there. There's the return address, which points back to 0x11AA, the instruction right after the call to vuln. This is the call to vuln that we just did before. So we now end up with the return address 0xAA here. We've created these two slots on the stack. So from unused, we created a base pointer, push RBP, that's this one, and then we adjusted the size to make space for the buffer for these 32 bytes. We now call put as to print out the string, get as to read in a string, which fills in the information into this buffer, just stores hi and a new line in there. So the total amount of how many bytes do we need in a buffer? Yeah? For what characters? So we're storing a total of 4 characters, H, I, new line, and a 0 byte, which determines the end of the string, right? So we've used the aerodynamic properties of candy is really horrible. So we've used 4 bytes out of 32 bytes. Good. The function terminates, we return, and we end the program. So far, so good. Now, if the vulnerable function runs and gets called, and the user input is A, lots of A, we fill up the buffer, but we also overwrite the stack frame of main. There's 0x4141414141, and the return instruction pointer pointing back to the code region with all 4 ones, which would result in like a violation. Allowing the attacker to hijack the control flow to an arbitrary location somewhere in the program. Right? If the attacker knows where they want to go to, either back to the original code or somewhere else, this would allow the attacker to hijack the actual control flow, because the attacker has overwritten the return address that was stored on the stack. So this return address, return instruction pointer here, that was stored on the stack, which was pointing back to the function here, now points to this address. And as we return from the function, the CPU will try to execute whatever is at this location. Now, this location is likely not mapped, and it will just crash. But the attacker, instead of submitting all A's, can also provide the byte values of the actual address that they want to target. There's one thing that they cannot enter. Oh, question?
The address, the return address, is like global on the machine, or is it on the program? So like, is the attacker who overwrites the return address accessing like whatever address in the machine, or something that is relative to the program, and so he can access like different parts of the program?
So this is for the current process, whatever is in the current process. If the attacker overwrites this in the kernel, it's anywhere on the machine. If the attacker overwrites this in a process, it is in the current process. So the attacker can redirect execution to any executable instruction in the current process.
I don't see how he can know where to point.
Now, by default, every time you start the program, everything will be at the same location. Right? So this allows the attacker to figure, like you can run it with a debugger, the program, and then just list where the program is being loaded at. And then you would know where the location actually is. Right? So this gives you an edge on the, through debugging. Right? Run it with a debugger, print, like what you're doing here is you run this in a debugger, and the debugger will tell you where these addresses actually are in the address space. Okay? This is an example of a buffer overflow. I will upload this so that you can play with it, just for demo. Or let me see if I can run a very, very quick demo on this. Okay. So give me a cookie. It prints some addresses. That was not what I wanted to type. Set arg stack cookie. You run this, and it tells you thanks for the cookie. Now we've seen the program before. If we run it as auth equals magic, and we add the correct white space as intended, it says, congratulations, you're authorized, because we've just set an environment variable to authorize the magic environment variable. So you see, this is pretty much the example that we had before. And I should make this bigger. If you cannot read this, let me know. If it would work. No, it did. Great. Better? Okay, so this is the script that we are running. We are setting authorized to 0, cookie 32.1. If the get environment auth is not equals null, and then we compare it to magic, we set authorized to 1. So this is just a fixed password that we run. We say give me a cookie, and then we do a string copy. This is the bug. Thanks for the cookie, and then here it's congratulations, you're authorized. So if we run this, There's something else. It just says, thanks for the cookie. If you run it with magic, it tells you you're authorized. But if you run it like this, cookies are delicious and tasty. Still the same, right? Thanks for the cookies are delicious and tasty. If we add a stop or one more characters, we're suddenly authorized. Right? Because we've written past the end of the buffer. We've now overwritten the authorized variable and set it to not 0. Now what we can also do is we can add a couple more characters. Still okay, right? We add a couple more dots. Still okay. We add a couple more dots, and suddenly, oh, a segmentation fault. What did we do? We started overwriting the return instruction pointer on the stack, which is not good, right? So, which means that by just providing a very long string, we can overwrite the return instruction pointer on the stack and thereby hijack control flow. I've written a little wrapper where I dump some shellcode that I wrote. Ignore this for now. It's just like the hex encoding of different instructions. And then I overwrite this and just execute the stack program with this information and data. Good? And it tells us, give me a cookie. It gives me the 2 addresses. Thanks for the AAAA. You see all the A's. And then you see a couple of question marks at the end. These question marks are the ASCII representation of the return instruction pointer that I encoded, which overwrote the return instruction pointer and allowed me to take control over the program. And now I can run commands in the shell that I've exploited in this program. Good? And that's a simple, very fast dry run of how to abuse and run an end-to-end control flow hijacking attack by overwriting the buffer. Past the end of the buffer, overwriting the authorized variable, and then overwriting the return instruction pointer to redirect it somewhere else. And you've seen the hex shellcode that I injected as a data variable, which then encoded individual instructions. So we've just simply redirected and pointed the return instruction pointer to the array where I encoded these instructions. And instructions are just individual bytes somewhere in memory. And if I know the address of these bytes, I can get code execution there. And this allows me to actually abuse the program in that way. How can we mitigate this? Well, if you look at possible defense strategies, right, as we are writing past the end of the buffer, we are violating memory safety. And here we've heard before, safe C, C++ dialects, soft bounds, memory safety, protection, or rewriting in a safe language. We could also enforce the integrity of certain code pointers because we've overwritten the return instruction pointer on the stack. There's code pointer integrity, data execution prevention, and whatnot. Randomization. Like every time we start the program, we can shuffle the address space a bit and make sure that every time you allocate data, you restart the program, it ends up in a different location. Flow integrity, such as data flow integrity or control flow integrity, we can validate right before an instruction pointer is being used that it is one of the valid locations that we allow from the program. If it doesn't work, if you don't catch it, it allows a control flow hijack attack. These top two, they are still interesting and hot research areas. I'll have to abuse a couple of minutes this time to go over time. I apologize in advance. The quiz question took me a bit too long to discuss. I hope that's okay with you. It's only 10 5 to 10 more minutes. As defenses for this, data execution prevention allows you to prohibit not the buffer overflow in itself, but it ensures that only areas in the address space that have been marked as code can be executed as code. Right? So that's a key difference. Otherwise, before data execution prevention, any byte in memory could potentially be executed. Right? So if you look at this without defenses, right, the attacker could inject or control any kind of data on the stack or on the heap that could be abused in a control flow hijacking attack. With data execution prevention, we are introducing an additional bit allowing us to distinguish between code and data in the address space, and only code can be executed by the CPU. Interestingly, luckily, we now have hardware support for data execution prevention, which makes this a great defense. Marketing departments had a blast. Intel calls this per page bit execute disable. AMD calls it enhanced virus protection. ARM calls it execute never. I don't know what AMD was smoking when they came up with the name, because it has nothing to do with the actual defense. But I guess whatever floats their boat. Address space layout randomization, which goes a bit into the question that you had. It's a practical form of address space randomization, and essentially every time we start a program, instead of mapping it as the same predetermined location, we shuffle it a bit and randomize it. For example, heap, stack, executable, and so on. They're all at random addresses. So here, again, without defenses on the left, a process would look like this. Everything is at well-known addresses: OX400, OX800, OXFFF. With ASLR, a couple of bits in the address are randomized each time you restart the process, making it extremely difficult to guess. So this is a probabilistic defense that makes attack much harder. An attacker will have to try many, many times. Now, if you combine ASLR and DEP, right, you have random addresses and non-executable data pages, which means that you're pretty much protected against a lot of the different attacks. Stack canaries are another defense. So early attacks overflowed the stack-based buffers to inject code, as we've just seen before. And a simple idea was to place a canary right before the buffer. I'll just go through the example here. Right? You remember this stack layout from before. Instead of just having the buffer, right? Instead of just allocating the buffer, we also allocate space for a canary. And in this example here, there's a few instructions that allocate the canary, which is a magic value that is being stored here. And right before we return, we check if the magic value is still correct, if the canary is still intact. So this goes back to the coal mines, where coal miners took a canary in a cage. If the canary died, the coal miners were supposed to get out as quickly as possible, because otherwise it would suffocate, because there's not enough oxygen in there. And canaries are much more reactive to the lack of oxygen, right? So it's a very good signal. And a canary, the idea of the canary is if you overwrite the canary, it's no longer the same value as before. And before you return from the function, you check if the canary is still the same. If it mismatches, you terminate the application. So if you overwrite everything with AAAA, then the program would abort with an error that says, hey, the canary is not correct. Yes?
But couldn't you bypass a canary if you know where it is and just add zeros to this?
You could bypass the canary if you knew what the canary was.
It's not always zero.
It's not always zero. It's a random, think of it as a random value that is stored on a per thread page. So this is a random value that is created at the start of the stack. Pseudo-random. Let's make it pseudo-random. Same question. Yeah, it's not all zeros, right? So it usually includes a zero plus a bunch of other things, but it's a semi-random random value. So this is very, very effective. Right? Protects against continuous buffer overflows by placing this canary between the buffer and any other data you have. it's usually stored in a safe location. So you compare between the safe location and the value that is on the stack. If it's not the same, right, you abort the program, as you see here, right? The stack smashing detected, terminated. Yes?
But these are not things that we as programmers can do.
No, this is done by the system in default. What you as a programmer can do is you don't disable these mitigations, and you're good, right? You would be surprised when we looked at Android how many libraries actively disable mitigations, which is, yeah, great. Yes?
Is the canary a fixed size or is it different?
It's 8 bytes on 64 bits, it's 4 bytes on 32-bit architectures.
So it's every time a fixed size.
Yes.
And that means you know the size, you can jump.
The canary only protects against continuous buffer overflows, not against arbitrary writes. Yes, good catch. Anything else regarding canaries? Then I'll quickly talk about limitations. We only covered stack-based buffer overflows, right? This was a very, very, very narrow glimpse into software security. As you mentioned, there's direct overwrites through pointer manipulation. There's heap-based buffer overflows, underflows instead of overflows, exception-based hijacking. There's a ton of other aspects. Exploitation essentially is an art, requires deep understanding. What we covered here in 30 minutes, there's a full course on this. If you're interested in that, there's CS412 in spring that I encourage you to take, which goes much, much, much more in depth. And allows us to go play through a lot of these examples in more detail. Let me summarize. So the software security aspect, lack of memory safety enables attacks. Be aware of the different attack vectors, such as the buffer overflows that we looked at, and how an attacker can hijack control flow, right? In the end, a process is just a flat area of memory that contains code, pointers, data, and everything else. An attacker that controls data may cause a program to interpret it as code by injecting code, overwriting pointers to redirect control flow to alternate locations. Mitigations limit the impact of vulnerabilities and try to make exploitation harder. Overall, trying to pinpoint and play with different angles.